Welcome back. We're in the middle of our logical programming units where we're using universal programming techniques. Now, it can be a lot of fun to just move the arrows around and see what kind of sequence emerge. But as we work towards more practical uses, we should stop to see if any things we create have practical meaning. We created one called a pullback. This was in a recent video. You may want to watch it before. Start with two arrows. Make a cone over those two arrows. The diagonal is already implied by composition. Then compare it to any competitor cone. You're universal if the competitor cone can map into your cone as an introduction rule. And there you have it. That commutative diagram is the entire pullback picture that we need to describe a new data type. The key idea of a pullback is that we have two functions, two arrows that meet at a common point. When this happens, we wanted to make a data type that took that in as its formation data and then created a new data type. The question is, does this represent something we might want to do in a real practical situation? I have behind me a toy, a simple example of how you can see this interaction. You will generalize this to numerous real practical uses. So I'm calling this the camping trip problem. In the camping trip problem, we see that there are two groups of arrows. This represents one function, and this represents a separate function. The data they're approaching over here is the possible ways to camp. We see that there's an option to camp under the stars with no shelter at all. There's also the option to camp in a tent or in an RV. What we now do is we assign the different ways that people get that information. For example, over here we have the Ferris family. The Ferris family has a young child and a dog. For them, it works better to use an RV. That's where that arrow goes. Part of the same function, but a different input, is Willie the worker. Willie the worker needs to be outside and needs to feel like they're really enjoying the outdoor air. For them, a tent is important. And finally, we have Henry the hiker. Only things that fit in the bag get to go. And so that makes it a tent. We now see that we've defined a function. That's one of the two arrows that will meet at a common point. That's the one I'll put on the horizontal line. On the vertical line, I have a different process altogether. I have the methods of finding ways to camp. For example, we have Ray's RVs. Ray's RVs will rent us an RV at a good rate. Meanwhile, we could go to a website to reserve a simple tent campsite. Both of these are now describing one unique function. This is one input leading to one output, another input leading to a different output. So what we really have are two functions, one vertically and one horizontally, and they're meeting at the same place. They don't consume all the outputs. That's not important. Now, what's the kind of storyline that you can imagine for a scenario like this? We have a group of campers with different goals in camping. We have a group of camp suppliers with different options to supply. The idea is to find a way to marry these two groups. At the moment, the two arrows don't know anything about each other. We obviously want these commercial products to match up with these consumers. And this is a general storyline you'll see in many situations of a pullback. You'll have one side which behaves somewhat like a supply and another side that behaves like a demand, and they're meeting some commodity. The goal now is to get them to talk to each other. But not just talk to each other in some silly way. We're interested in the maximal way to make the assignment. We're interested in seeing all the possible combinations that could solve this problem for as many people as possible and as many suppliers as possible. Let's look at Willie the worker. Willie the worker was only interested in tent camping. Therefore, Willie the worker will have to go through the website. Henry the hiker has the same goal in mind. They too will need the website. The Ferris family was the one that was interested in RVs. They would go to Ray's RVs. Now, what I've created is a new data type. It's an example of a pullback type. We couldn't have built it without inspecting the two functions we were given. We effectively looked at how they move the data around and pulled back to create a new data type, which is the matchings of who wants to go with what type of commodity. Now we have to do is connect them to the data we already have, the functions that are already present. We have a new data type. It's going to need elimination rules and introduction rules. A straightforward way to do this is to map them downward by take the first value. This is similar to our pi A when we had a pair type, just the first component. How do we get to the commodities, the suppliers? Well, the second component. So we now have created elimination rules of our new data type. This is setting up the picture we expected for our commutative diagrams for the pullbacks. It's created a cone of our two arrows. We take the two arrows mapping to a single point, and we make a cone by two arrows mapping to the two endpoints. That makes a square. Pay attention to the direction of the arrows. They can go forward, backwards, up, or down. It's the direction they point that matters. So, we've just taken our two-story problem functions and created a data type, this pullback. But we haven't quite finished. All we have so far in our data type is how to get information out of it. How do we put information in? So let's zoom out and see what we're still missing. I've added some clouds around the data we have because I want to articulate more honestly what's going on. While it may be that we have two examples of suppliers, we could assume that there could be many, many more. The whole point of the program is to anticipate there will be data we don't yet know about. Likewise, we can't assume we've seen all the customers either. So what we had was a representation of a few examples from some larger clouds, some larger types of data. So if we now articulate this more accurately, this cloud of data is the data type for camping methods. It's the commodity that things are going to share in the story problem. Here is our suppliers, which include the website and Gray's RVs, but it could have many other things like Tony's trailers. Whatever we add to this picture stays in that type. Whatever campers we add stay in the camper type. We're in the middle of creating our own new type called the pullback. And what we've done is give 3 examples of data of that type, but that's not enough to know everything. We have to anticipate that we're going to need to introduce new parts of that data type, new instances, which means we need an introduction rule. Based on what? Based on new data. The new data lies outside. The new data is some new information that informs us about some new suppliers or some new campers. Well, let's now take the scenario that we've got something here that's assigning some set of suppliers and some set of campers, and they have to work with the 2 prescribed functions that we have here. What would we do? Is we would start to add to our list. If we discovered that Tony's trailers could also be used, we could instead have a new part here where maybe the Ferris map could also use Tony's trailers. We would add that in. And so that's the introduction of a new term. Now, where did that data actually come from? It came from the knowledge that we had a new supplier, this Tony's trailers. This is the key idea of the pullback diagram. Whenever somebody provides us with some other options, bigger functions, they should be able to get and introduce data of our kind. If they can always convert their data into our data, then we have conquered the universal puzzle. Our data type is ready to update to these new challenges. This is the nature of many great programs. When you design for your future, you're often designing with a universal property in the background. You're designing for the eventual need to update the things you've already solved. When you create this, it's easiest to sit back and erase the actual questions. Think of these as simple types with simple arrows. Draw the diagrams that commute, and you'll see the general architecture. It can also be the case where once you've solved the problem with one type of technique, one universal program, you could use that universal style on many new problems. But a bit of warning. Too much abstraction can be hard to follow. If someone doesn't have experience with universal programs, and you tell them this is a standard pullback diagram, they may not know what you're describing. Keep in mind that a good example should also be accompanied with any abstraction. Otherwise, people may not know what to do to fix a program if it's broken, or they might not even realize that it's not broken, but they just aren't using it properly. The key ideas of universal properties are the foundations of good data designs, but don't leave behind all the good data that you need for explaining things to other people. Examples and documentation should always come along with the formalism. So there we have it. This is a story about camping, which illustrates the pullback diagram. We have basically the supply and demand story. This is something that will happen in many production lines. The key ideas here are that we have 2 functions that lead to the same commodity, in this case, the camping methods, and they don't know about each other. The pullback diagram is the way to make a data type that relates both functions together and the data they contain, and it does so in a way that's universal. So any future updates can simply be folded in as new introduced data types. Once you have this under your belt, imagine flipping the arrows. That is, suppose that we have one piece of data that leads to 2 others. The arrows are pointing the opposite direction. What would this mean? 2 events are being caused by the same initial event. What is the result of putting them together? When you get these metaphors under your belt, you'll start to have a language to talk about deciphering individual problems by looking for these kinds of relationships. Is something occurring simultaneously from some root cause, or is it that we have some shared resource like supply and demand? If we break our problems up into dots and arrows, we can often find that gluing together these little simple ideas can make all the data types we need to take apart any large complex flowchart into simple universal data types. Until next time. That's how you take care of your chalkboard.